friends, welcome back. Now we are going to discuss about a very important topic that is phase diagrams. So let us go. So in the second unit, that is phase diagrams, we will be discussing about what is a solid solution, what are the rules for substitutional and interstitial solid solutions, and this is going to be a detailed discussion on different types of phase diagrams and how we are going to interpret. And the most important thing in the entire course of engineering metallurgy is about the iron carbide phase diagram, and we're going to discuss in detail about the iron carbide phase diagram, microstructural aspects of it, and followed by few of the important structures and the reactions, of course. So all right. So let's dive deep into the understanding about what is a pure metal, and then we'll go into what is an alloy. So, as it is mentioned earlier, this is a metal which is having a metallic bond. And when I say pure metal, it is having only one element. That means it can be either pure iron, pure copper, pure in the form of tungsten, aluminium, so on and so forth. So when it comes to pure metal, they have limited characteristics, limited properties because there is only one element. So that element may be good in maybe electrical conductivity, ductility, or corrosion resistance, but it is having one or maybe two, but it is having independent properties, which can not be improved or enhanced because it is a pure metal made of only single entity. And so when it comes to an alloy, unlike in case of pure metal, we want some of the additional properties that has to be incorporated into an alloy. That is the basic reason. For example, let's take an instance of pure iron. Iron in the purest form will have lot of disadvantages because it readily oxides with the oxygen in the environment and it forms a ferrous oxide, which is nothing but a rust. So we firstly, the process of making into the purest form is very tedious and costly affair. Second is to maintain it at that 100% pure form is also very costly affair because we need to enclose it and see that it doesn't oxide. So that's where we want the iron, that is pure iron, to have certain other additional characteristics. Moreover, the pure iron form will have very limited strength or ductility, malleability properties. So that's where we come into the picture of an alloy. When we alloy it, we try to bring in more properties into the iron, maybe some pure metal. So combination of two or more elements, of which one element should be a metal, is a major as a major portion is the definition of an alloy. So when it comes to brass or steel, that's where we alloy it with other additional elements. For example, when zinc is alloyed with the copper, it gives us brass. And when copper is alloyed with steel, we get, sorry, iron, we get steel. So this is how we try to understand which element is to be paired with the other element so that we get the best alloyed properties. And that is what we are going to discuss today. So moving on. So when we say pure element and when we say an alloy, this is nothing but when you correlate, it is also a kind of a solution. As we have it in liquids, even in the solids, we may have a certain amount of solution, which is a combination of solute and solvent, like how we have it in the liquid. So it can be called as a solid solution, which is nothing but an alloy in which solute atoms are distributed in the solvent matrix and has some same structure of the solvent. So that is called solid solution. Apart from pure metals and solid solutions, you may also have certain amount of intermediate phases which are formed between two dissimilar elements having widely divergent electrochemical properties. So they are called as intermediate phases. So we'll be discussing all these things. Of course, we understand what is a pure metal. So we have what it takes to form a pure metal, its limitations to be precise. We also know that alloy, which is also called as a solid solution, is a combination of two or more metals. And when we have a distinguished properties or very two dissimilar elements having widely divergent properties, then it is called as an intermediate phase. So that's what is the classification. Now, Furthermore, if you divide it, it can be called as homogeneous or a mixture. When it is homogeneous, that means it is homogeneously same across any phase. So this is homogeneity, and this homogeneous can be of again two types, that is a complete solid solution or a compound. The basic difference between solid solution and compound is solid solution is something which is having same properties as of that of a parent metal. That means, suppose, for example, we take element A and element B, and this element A and element B are combined to form a solid solution. It is expected to have the properties of A and B, and it will also have that AB will have the properties of A and B. That is a solid solution. Whereas in case of a compound, it is the intermediate alloy phase. Like we discussed in the previous slide, in the intermediate alloy phase, we have divergent properties which are dissimilar to that of A and B. So that AB, whatever the product we got, that will have distinguished properties or deviating properties than that of a parent element. Then it is called as a compound. Further, solid solution is having two types, which is substitutional type or interstitial type. So we have already discussed this in the defects. Uh, it comes under point defects, non-ionic, wherein the substitutional is taking the atoms by an foreign atom in the substitutional regular position, and whereas interstitial is occupying the intermediate alloy, sorry, atom position, that is called interstitial type. And mixture is something where we have a compound intermediate alloy phases present. So that is called a mixture all. We have several phases present in that. And when it comes to solid solution, in the solid solution, we have, like we discussed, two types. One is substitutional type, and another one is an interstitial type. When it comes to substitution, the substitution of element A and element B may be either an orderly manner or disorder. When I say disorder, it is like you have very random nature of the substitution taking place. So, like you can see here, element A, element B are substituted randomly. But there can be certain alloys which can be very regular, orderly manner, like in aluminium and copper. So the arrangement is order. That is called type of solid solution. So this is what belongs to substitutional. So the idea is very simple, like how we have it in the defects, in the point defects. There, they are not deliberately added. They are present because of a defect in a point. Whereas in case of alloy, here deliberately, intentionally, we add the element of other nature in order to form a solid solution. So that is called substitutional type of solid solution. So they take the regular positions of element A. When it comes to interstitial, this is the space in between the atoms. So when these interstitial spaces are occupied by other element, that is called interstitial type of solid solution. So, in order to give a valid rule for formation of the solid solubility, for substitutional type, the rule is given by Hume-Rutre, which is having four major points. First one is the relative size difference. The size difference between the solute and the solvent atomic size cannot differ more than 15%. That is the first point. Second one is the chemical affinity or electronegativity. That is, there should be not much difference between the positions or the electrochemical negativity. That is nothing but when we have it in the periodic table, the element selected cannot be far off because that defines the electronegativity nature. Then the third one is a relative valency. That is the outermost electronic configuration of solute and solvent must be same. And the last one, very important, that is the crystal type. Both the solute and the solvent should have the same crystal type. So this is defined by Hume-Rutre, and it is for the substitution type of solid solution. So when it comes to interstitial type, we have only one rule, that is the uh, size of this solute atom must be very, very small. it has to be less than 1 Armstrong. If the atom is less than 1 Armstrong, then it is convenient to form the interstitial type of solid solution. That's all. Whereas in case of uh, substitutional type, you have four rules given by Himrutre. On the other hand, for the interstitial type, we have only one rule, that the size of the solute atom must be less than 1 Armstrong. So this is the definition or rule for the formation of solid solubility. So I'll pause here, I'll stop here so that you will have a clear understanding. In the next class, we'll be discussing further on the formation of phase diagrams and all. Thank you. Thank you for watching.